Hello, welcome again. We are solving GATE 2020 Mechanical Engineering Paper 2. Question number 37 is a hollow spherical ball of radius 20 centimeter floats in still water with half of its volume submerged. Taking the density of water 1000 kilogram per meter cube and the acceleration due to gravity as 10 meter per second square, the natural frequency of small oscillation of ball normal to the water surface is dash radian per second. Round off to 2 decimal place. Okay. Now let Ri be the inner radius of the ball and R naught be the outer radius of the ball. That is given as 20 centimeter. Okay. So volume of the ball material is 4 by 3 pi R naught cube minus Ri cube. Okay. So that is the volume of material of the ball. Okay. And let rho be the density of the ball. Then the mass of the ball is volume and volume of material. Density and volume of material. Then it is mass of ball. We multiply it by g. Then it is the weight of the ball. Okay. Now this is the weight of the ball. Okay. And this is the volume of the ball material, and this is R naught is your 20 centimeter. Okay. So now when the ball is in water, then so this is the ball. Okay. And it is in water. Okay. So as the density of the ball is not given. Okay. Density of the ball is not given. So let us assume that it doesn't it doesn't fully submerge. It does not fully submerge in water. Okay. So it is partially submerged in water. Okay. So then in that condition, the weight of the ball will be equal to the buoyant force. Okay. So this is the weight of the ball. Okay. So weight of the ball is the buoyant force exerted by the water. Okay. And so water, the weight is exerted by the ball and buoyant force is exerted by the water. Okay. So and buoyant force is volume of water displaced. Volume of water displaced. Okay. Buoyant force is volume of water displaced into density of water. Okay. Or we can say it is weight of water displaced. Okay. And weight of water displaced is the weight of water displaced is volume of ball inside the water, and volume of ball inside the water, and multi, and multiplied by density. Okay. And it is given that with half of its volume is submerged. Okay. So as so external volume of the ball is your 4 pi R naught cube. Okay. So its half of the volume is submerged in water. Okay. So it is the volume submerged in water. Okay. And or it is the volume of water displaced. Okay. So if we multiply it by density of water, okay, and g, okay, then it is the buoyant force. Okay. This is the volume of the ball inside the water, or volume of water displaced. Okay. And this will be your buoyant force, volume of water displaced into rho g. Okay. So this is your buoyant force. Okay. And this is buoyant force, and this is equal to weight of ball. Okay. Because buoyant force at a weight of ball and buoyant force are equal. Equating this one and equating this two, equating this one and two, we get rho b is density of ball and rho is density of water. Okay. So we get the relationship between rho b and various radius. So rho b R naught cube minus Ri cube bracket rho R naught cube by 2. So this is equation number 3. Okay. Now this ball is suppose submerged. This ball is suppose given a displacement x. Okay. to find out the frequency, let a small displacement is given to the ball in the downward direction. Okay, so its velocity will be in downward direction and its acceleration will also be in downward direction. So inertia force will be in upward direction. Okay, so this is the inertia force. Okay, now as the ball is submerged in water by small amount x, so uh, the more water will be displaced, so there will be increase in buoyant force also. Okay, so the buoyant force will act, that small buoyant force that is caused due to displacement of this ball, displacement x of this ball inside water is in upward direction. Okay, and this small buoyant force is nothing but area, this from above it will appear as a circle area, pi r square, outer circle pi r not square, and multiplied by x. X is displacement. Okay, so the small buoyant force is pi r naught square x into rho g. Rho is density of water and g is acceleration due to gravity. Okay, so this small buoyant force will be equal to volume of ball that goes inside the water with displacement x. Okay, that is pi r naught square x rho g. Okay, so that is small buoyant force. Okay, now now this buoyant force will also act in upward direction. So the equilibrium condition is mx double dot plus rho g pi r naught square x. Okay, so here the coefficient of x is this and the coefficient of x double dot is m. So omega becomes as this rho g pi r naught square m. Okay, so m is nothing but mass of m is your mass of ball, and mass of ball we have calculated, that is 4 by 3 pi r naught cube minus r cube ri cube rho b. Okay, or now this we have this relationship, rho b r naught cube minus ri cube. So we can put this rho b r naught cube minus ri cube as rho r naught cube. Okay, by 2. Okay, so from this we can get mass in terms of r naught and rho. If we put this mass here, then we get the this 3 by 2 g by r naught. Okay, so g is your 10, r naught is 8.2. So putting the value we can get omega as 8.66 radian per second. Okay, so answer is 8.66 radian per second. Next, uniaxial compression test data for a solid metal bar of length L 1 meter is shown in figure. So this is the figure given. This is 130 MPa, this is 100 MPa, this is 0.002, this is 0.05, and this is strain, this is stress. Okay, the bar material has a linear elastic response from O to P followed by a non-linear response. The point P represents the yield point of the material. The rod is pinned at both the end minimum diameter of the bar so that it does not buckle under the axial loading before reaching the yield point is dash mm. Round up to 1 decimal. Okay, so for pin jointed end we have this formula, that is pi square ei by l square. Okay, so we need E here. So E can be calculated by this 100 MPa stress divided by this strain. So E is your this 100 by 0.02, that is 50,000 MPa. So L is your L is given. L is 1 meter. Okay, or 1000 mm. Okay, so we can calculate buckling load. Okay, and I is your pi by 64 d4. In terms of d4 we can calculate buckling load. Okay, now the load at this point is stress at this point is 100 MPa and load is your 100 by area. Okay, so sorry, 100 into area. So this will be 100 into pi by 40 square. So this load should not exceed this load. Okay, so equating these two, we can find out diameter d. Okay, so this is also in terms of d. This is also in terms of d. So the answer is 56.94.